Hey, welcome back to Math with Patrick. Today is September 17th, and we're solving problem 260 from the Daily Epsilon calendar. And of course, we're joined by our very special guest, Quill, my cat. He'll be helping out with the integral today. And apparently the answer is supposed to be 17, or I guess about 17, because it's asking us to round our answer, because the answers in this calendar always match today's date. So we have an integral. The bounds are from 0 to 2, and our integrand is 16x to the fourth over 9 minus x squared dx at the end. Okay. So there's a lot of strategies that you could use to solve integrals. There's u substitution, there's integration by parts. I think the best one for this problem today is partial fraction decomposition, because I noticed that the denominator is factorable. And hopefully, by finding the partial fractions of our integrand, we can have easier integrals than this one. The idea behind partial fraction integration is, well, needing to know something about partial fractions, where if you have a factorable denominator, it is possible to rewrite it with the factors of the denominator, maybe a plus or a minus sign in the middle. And I don't really know what these numerators are supposed to be. I would have to do a little bit of figuring out. I mean, we could multiply both sides by 15 here. So we get 7 is equal to 3a plus 5b. And then I'd kind of need to play this game of adding or putting numbers for a and b until I get the value 7. I think for this one, I might even need a minus sign. It looks like if this is a 10 and that's a -3, I get what I want. So I guess I would actually need either a negative numerator here and a positive numerator. Let's see, b was supposed to be 10, no, 2, right? Something like this. Hold on. A is supposed to be, -1. There we go. Okay. So this hopefully would actually give me a true equation. It just takes a little bit of work to figure out what these numerators are. So we could play the same game with our integral, where let's factor the denominator and then play that partial fraction game, and hopefully we get easier integrals out of it. The first thing I am going to do, though, is I am going to factor out that negative sign from the denominator. I mean, technically what I'm doing is I know that when I swap the minuend and the subtrahend in a difference, I essentially produce a negative sign. So these two things are equal. I need that negative sign to compensate for the fact that I swapped them. And then anytime that you have some kind of multiplier on the inside of an integral, you can totally just take it out, including that -1. So that's what I'm doing, kind of 2 steps at once, is just flipping that denominator, just because I like having that x squared term be positive, and removing the negative sign out front, because I don't like dealing with unnecessary coefficients in my integrand. We could factor the denominator there. This is a difference of squares, and so I know I can factor it as x plus 3 and then x minus 3. And then I'm setting myself up to do that partial fraction decomposition, where I just need to find those new numerators to match the same expression as before. So essentially what I'm doing, I'm claiming that I could find a numerator for this fraction and find another numerator for that fraction so that it equals exactly what we had before. And let's just write that denominator in factored form. One thing I could do to start solving for a and b is to multiply both sides by the denominator. I did this in the last example with that 15, right? I just multiplied both sides by 15. So it just looks a little bit different now that we're working with variables and stuff. On the right side, these denominators just cancel, and so I'm left with 16x to the fourth. On the left side, when I distribute this, maybe you'll notice that this x plus 3 in the bottom does cancel with this x plus 3 on the top. So I'm just left with x minus 3 times a. And then a similar thing will happen with our b over here, where we're just left with an x plus 3, and then times b. I guess I could distribute this a times x minus 3a plus bx plus 3b is equal to 16x to the fourth. Well, we have 4 terms on the left, and somehow they're supposed to only equal 1 on the right. So I think it'd be really convenient if those 2 terms canceled right there. So it would be really nice if a was the same thing as b, then those would just cancel out. So if that's true, I would get ax plus ax equals 16x to the fourth. That's just 2 ax's equals 16x to the fourth. And I guess the whole point is isolating a. So if I divide both sides by 2x, a is going to be equal to 8x cubed, which is the same thing as b. And then that would work out, right? Because these would both be like, what, 24x cubed. And so those 2 terms would cancel out with each other. So that's cool. Both a and b are going to be 8x cubed. 8x cubed, 8x cubed. All right. And maybe one more thing we could do before trying to kind of solve these integrals is we could factor that 8 out from both of our fractions. And then since it's just like this coefficient, we can factor it way out of our integral. And so I could do like a -8 out front. And maybe at this point, let's split our integral into the first one, which will be x cubed over x plus 3 dx. And then our second one, integral still from 0 to 2, x cubed on top, x minus 3 on bottom, dx. Close that bracket because I want to multiply 8 by whatever this is. And so I'm noticing here that once we evaluate all of this, I'm hoping for a number like maybe a little bit less than -2. Like if it's -2, we'd multiply them together and get positive 16, right? -8 times -2. So if we make it a little bit less, like a -2.2, that's roughly where we should be getting because it's a rounded answer in the end. So something a little bit less than -2 would be great out of this kind of sum of integrals over here. And one thing I'd like to do is I'd actually like to get just an x in the bottom. One thing I know about this kind of setup right here is it's okay to kind of rename this fraction kind of like this. And I don't know if it's actually going to be like an x minus 3 or an x plus 3 on the top. But the idea is I'm essentially just shifting all of my numbers 3 to either the left or the right. And then I know that I can expand this and just divide each of the terms by x, and I will get an evaluatable integral. So here, let's introduce maybe different variables. We could say like s is equal to, or actually, how about maybe s minus 3 equals x? Because then when I plug this in right there, I will get s minus 3 plus 3. And so I will just get that s in the bottom that I wanted. So let's keep the -8. Let's keep our bounds empty because I think I'll have to change the bounds. And then here, this just puts an s on the bottom. And now that x is the same as s minus 3, I could replace it there, put on a cubed. Oh, and then if we take the derivative of both sides of this equation, we're going to get something that looks like this. The derivative of x is just 1. The derivative of this minus 3 is 0. And so I get ds dx equals 1. And then we can do that thing that we're technically not supposed to do, which is multiply both sides by dx, just to show that ds and dx are equivalent in some way. And so I could replace my dx with a ds right there. And I do need to change the bounds. 0 and 2 are bounds in terms of x. So I will need to plug in that 0 right there and see what value of s I need to kind of get to that 0. And I can see that 3 minus 3 is 0. So this lower bound should be 3. And by the same logic, this upper bound should be 5. Cool. So it looks like I just added 3 to both numbers for my bounds. So for my other integral, let's name it maybe r plus 3 equals x. So I'll get an r on the bottom and r plus 3 cubed in the numerator. And then my bounds, well, if this one I added 3, for this one I should probably subtract 3. So we'll go -3 to -1. Well, I think we should just expand those numerators and then just kind of run through that fundamental theorem of calculus where we take the antiderivative of our integrands, plug in the upper bound, plug in the lower bound and then subtract those two values. We'll have to do that for each integral. So let's move that negative 8 over here. I think I'll need a lot of room for this one. I know that doing s minus 3 squared will give me s squared minus 6s plus 9. I just don't have the cubing thing memorized, so I'll just multiply it all out here. This is s cubed. That's minus 3s squared minus 6s squared, so overall minus 9s squared. This is plus 18s plus 9s, so that's plus 27s. And then finally we get a minus 27. Cool, and then we divide all that by s. So actually each of these terms I could then divide by s. I'm kind of like distributing that denominator to each one of these. So I do get s squared minus 9s plus 27 minus 27 over s. And it was kind of nice to do this one first because the other integral on the right here is just going to do the exact same thing. But since there's a plus sign in here, ds. Since there's a plus sign in here, I don't have this kind of alternating plus minus. I'll just have a positive r squared, a positive 9r, a positive 27, and then a positive 27 over r dr. And bracket, because I still want to multiply by that negative 8 in the end. Here, let's take the antiderivative of each of our terms. We're going to get 1/3 s cubed minus 9 halves s squared plus 27s minus the natural log, minus 27 times the natural log of the absolute value of s. Evaluate that from 3 to 5. Still want that negative 8. Then we're adding basically the same thing, but then we're going to evaluate these from negative 3 to negative 1. So 1/3 r cubed plus 9 halves r squared plus 27r plus 27 natural log of the absolute value of r. Okay, there we go. And close parentheses. So it's going to take a while. We need to plug in the upper bound, plug in the lower bound, and subtract those two values and do it for both of these. So I'm just going to speed through all the calculations. Let's see. Okay, 5 cubed, 125. 1/3 goes there. 5 squared, 25 times 9, 175. Divide by 2. 27 times 5 is 135. And then minus 27 natural log of 5. We're going to subtract what happens when we plug in the 3. 27 divided by 3 is 9. Negative sign, 9 times 9 is 81 over 2. 27 times 3 is another 81. 27 natural log 3. Cool. Adding, plug in the negative 1. That is a negative 1/3. This is a positive 9 halves. This is, a negative 27. This is a positive 27 natural log of 1. This natural log of 1 equals 0. So I could just erase that term, but I am going to just cross it off just so I know that I have it and I don't need to worry about it because it is 0 times 27, which is 0. Plugging in the negative 3 here, minus all of this. Plugging the negative 3 is negative 27 divided by 3 is negative 9. 81 over 2 again. This is a minus 81. This is a plus 27 natural log of positive 3. Okay, let's maybe distribute these negative signs just so I'm very careful about the signs of everything. So distribute the one on the left, distributing the one on the right. Hopefully we get some cancellations here because I really don't want to do all this arithmetic. I'm already done a lot. Okay, we do actually. I think both of these bottom ones completely cancel. Here's a positive and a minus. Here's a minus and a plus. Plus, minus, minus, plus. So those bottom terms fully cancel out. And we're just left with whatever's on the top. And we have a whole bunch of random rational numbers. And then minus this 27 natural log of 5. So let me just stick all this in a calculator. And we'll just figure out what fraction it's supposed to be. And I'll get back to you. So I added up all the numbers. Also, I did catch the 225 there. I went the wrong way on a number of quarters. I was thinking, okay, 8 quarters is $2. And then for some reason, I just went down 1 instead of up 1. Anyways, it's 124 thirds. And so this is our exact answer for today, not forgetting that times negative 8 on the outside. And here it's just asking us to round this answer. So it doesn't really matter that we got an exact form answer. So I will divide by 3. That's around 41. I'm going to subtract the 27 times natural log of 5. And earlier I said I'm hoping that this number is a little bit less than negative 2. And cool, it is. I guess it's negative 2.1 instead of negative 2.2. And so if we multiply this by a negative 8, we get 16.97 for today, which to me is pretty darn close to 17, which is today's date. So at some point through all these calculations, you do have to pull out a calculator. For me, I wanted to know some nice, concise answer in an exact form. But honestly, right around here, I would say it's totally fine to just whip out the calculator, because this is just a lot of plugging in and fortunately, a lot of cancellations. But ultimately, our answer is this, which rounds to 17. So I'm all done for today. Thank you for coming along for this slightly longer video than usual, and I'll see you tomorrow. Bye.